Hey everyone, welcome to today's Explainer. We're diving straight into a massive breakthrough from NVIDIA that tackles one of the absolute biggest bottlenecks in AI text generation. They call it the Nemotron-Labs-TwoTower model, and it completely reimagines how large language models actually generate the words you read on your screen.
So here's the million-dollar question for you. Can we actually make AI generate text twice as fast without trashing the quality? I mean, think about that universal frustration of using an AI chatbot and watching it type out its answers one single word at a time. It's kind of like watching someone hunt and peck on a typewriter when all you want is a 50-line Python script right now. We all want faster responses, but historically, pushing for pure speed has meant sacrificing the intelligence and accuracy of the model. Well, NVIDIA's new architecture is attempting to shatter that compromise entirely.
All right, let's dive into this. Here's our roadmap for today. First, we'll look at the AI speed bottleneck, then enter the two-tower architecture. See how the towers connect, check out the benchmarks for speed versus quality, explore some real-world use cases, and wrap up with the strengths and weaknesses. To really appreciate the solution here, we've got to understand the problem first. So, Section 1, the AI speed bottleneck. Right now, the vast majority of language models out there are autoregressive, or AR for short. Basically, they decode and generate text sequentially, strictly one single token at a time. This serial process creates a hard mathematical cap on generation throughput. You literally cannot generate the 10th token until you have completely finished generating the 9th one. Now contrast that traditional brick-by-brick AR method with discrete diffusion language models. Diffusion doesn't work sequentially. Instead, it generates multiple tokens in parallel and refines them iteratively. It's kind of like slapping a whole row of rough, messy text onto a page all at once and then slowly bringing the entire thing into sharp focus at the exact same time. That's diffusion. Which brings us perfectly to Section 2, enter the two-tower architecture. NVIDIA's Nemotron-Labs-TwoTower is this brilliant hybrid that brings both of those worlds together. And the scale of this open-weight model, it's just massive. We're talking roughly 60 billion total parameters across both of its towers. This isn't just some tiny, experimental proof of concept. It is a heavy-duty, commercial-ready architecture. So, what's under the hood? Well, the crucial point is that it's built on the Nemotron 3 Nano 30B backbone, which was pre-trained on a staggering 25 trillion tokens. Picture this. Each tower has 52 distinct layers, and they interleave Mamba 2, self-attention, and a mixture of experts setup featuring 128 routable experts. It is an absolutely rock-solid starting point. But hey, having two massive towers doesn't mean much if they can't talk to each other, right? Let's move to Section 3, how the towers connect. This connection right here is the absolute core of NVIDIA's breakthrough. Two-tower literally splits the generation job into two distinct roles. First up, we have the AR context tower. This one is completely frozen. It wasn't trained any further. Its only job is to causally process the prompt and any committed tokens to keep that standard autoregressive capability perfectly intact. Then, you've got the diffusion denoiser tower. This guy was trained on an additional 2.1 trillion tokens. Its job is to look at a messy block of text and refine it using bidirectional in-block attention. So basically, one tower holds the context, and the other cleans up the mess. Let's walk through how this actually plays out when generating text. It runs block by block. Step 1. The model spits out a block of blank mask tokens. Let's call the number of tokens S. Step 2. The denoiser tower refines that block over a specific number of steps called T. Step 3. Any tokens that hit a certain confidence threshold are officially committed. And finally, Step 4. The context tower processes those newly committed tokens and updates its cache. Because it's refining whole blocks like this, two-tower can commit multiple tokens per step right out of the gate, easily crushing that slow, one token at a time AR crawl. And this brilliantly illustrates why NVIDIA's specific engineering matters so much. Older diffusion methods used to just broadcast the very last hidden state of the network. But here, denoiser layer I cross-attends directly to context layer I. This layer-aligned setup gives the denoiser multi-scale access to literally everything the context tower is thinking at every single level of the network. Okay, theory is great and all, but does it actually work in practice? Let's transition to Section 4 and look at the benchmarks, speed versus quality. Take a look at this massive jump. When they ran two-tower on two H100 GPUs at the default confidence threshold, it hit a 2.42x increase in wall clock generation throughput compared to the standard AR baseline. That is nearly 2.5 times faster in actual real-world time. Just incredible.
But remember, our big question from the start, can we get this speed without trashing the quality? Well, the data has the answer. Even while running at that blazing 2.42x speed, Nemotron-Labs-TwoTower retains 98.7% of the AR baseline's aggregate benchmark quality. You're getting a massive speed boost with almost zero penalty to the model's overall intelligence. That's a real game changer.
If we break down the specific tests, we do see a little nuance. For general knowledge tasks like the MMLU, the scores stay practically identical, 78.56 versus 78.24. But actually, if you look closely, there is a modest drop when it comes to highly specific code and math tasks. On the human eval coding benchmark, it goes from 79.27 down to 75.58, and math drops a couple of points on the GSM-8K too. So general reasoning is completely solid, but complex logic takes a tiny hit for that speed.
So, what does this all mean for the people actually building things? Let's bring it back down to earth in Section 5, Real-World Use Cases. What's super convenient here is that this single checkpoint exposes 3 different inference paths. Developers can use the Generate Mask Diffusion mode to commit full blocks of text per step for maximum speed. Or, if they need to, they can drop back down and use mock AR or standard AR generation to fall back into that traditional one token at a time decoding. You get all this flexibility without having to load entirely different models into memory. The whole shebang in one package. Practically speaking, this opens up some really cool doors. Say you're on a data team generating massive batches of synthetic text. You can purposely trade a tiny 1.3% drop in quality for a 2.42x speed boost just by tweaking the confidence threshold, which they call gamma. Want higher quality? Raise the threshold. Want pure speed? Lower it so you commit more tokens at once. Plus, since the context tower keeps its original language model head, it's a perfect drop-in for speculative decoding pipelines.
As we get ready to wrap up this explainer, let's take a balanced look at the real-world trade-offs. Section 6. Strengths and Weaknesses.
On the strength side, honestly, it's phenomenal. It ships with open weights under the Nemotron Open Model License, which means it's ready for commercial use right out of the gate. You get incredible speed and highly efficient training, 2.1 trillion tokens for the denoiser. But let's be real, on the weaknesses side, there is a serious hardware tax here. Keeping 2 30 billion parameter towers loaded in memory definitely spikes your fixed footprint. To run the full 2-tower diffusion in BF16, you're going to need 2 GPUs, using about 59 gigabytes of memory each. And as we saw earlier, you do have to accept that slight dip in coding and math capabilities.
But looking at the big picture, the core takeaway of this explainer is absolutely clear. NVIDIA's Nemotron-Labs-TwoTower successfully bridges that gap between the high quality of autoregressive models and the lightning-fast parallel speed of diffusion. It proves, for sure, that we don't have to be stuck behind that one token at a time bottleneck forever.
Which leaves us with one final thought for you. As this hybrid officially shatters the old AR speed limits, what new, real-time AI applications will you build with this open-weight model? When speed is no longer the bottleneck, the possibilities change entirely. Thank you so much for joining me for today's explainer, and keep exploring.